Good times, my dear students. Welcome to the today's session. Today we are once again discussing the same topic, that is resonance. Resonance has different meanings depend upon the at what context we are using. In physics, it is related to sound, vibration. So here in chemistry, resonance means it is also a kind of vibration, but actually it is movement of electrons. In vibration also it moves, something moves. So here also electron moves. So it is movement of electron to take some position in the structure that comes under the resonance. So resonance means it is the moving of electrons. Now, which electron will move? It is the pi electron, or it is the lone pair of electrons. They move because they are free. Yesterday I told in the previous class, out of the two bonds, if it is going for the double bond, out of the one is sigma bond and one is pi bond. Sigma bond is very strong bond because it is the direct overlapping, direct interactions, whereas pi bond forms because of the side interactions. That's why it is not so strong. When it is not so strong, then it keeps moving, depend upon the requirement. That becomes resonance. So we understood in the previous class how to draw a Lewis structure for a particular molecule. So in some cases, okay, especially in the case of covalent bonding, for us it is very difficult to draw same single Lewis structure for the molecule. More than one possibilities are there. That time the concept of resonance comes into the picture. So resonance is there where pi electrons or the lone pair of electrons start moving. So already explained yesterday by taking an example. Now today let us discuss the same by taking the example of what? SO2 molecule, sulfur dioxide molecule. This is our sulfur dioxide molecule. Okay. Sulfur dioxide contains two different kinds of atoms. One is sulfur, one is O. And the formula is SO2. O, how many valence electrons? 6. Yes, how many valence electrons? Again 6. First we will check whether each O has 6 each O and each S having 6 electrons or not. This O 1, 2, 3, 4, 5, 6. 6 are here. Around this O 1, 2, 3, 4, 5, 6 are busy in the bonding. Okay, totally 6 here. Now sulfur also belongs to the same family, oxygen family. So number of valence electrons equal to 6 here also. Where are those 6? 1, 2 which are free. This is third. This is fourth bonding. This is fifth bonding. Out of 6, 5 are here. Where the sixth one has gone? Kindly check here. It is here. Why? This oxygen should have how many electrons? 6, no? Already 6 are there here. What about this electron which is busy in the bonding? So this is 7th electron. So why 7th electron came here? Just to fulfill the octet, which is called stability. Okay. So this S has given its 6th electron to this O so that this O goes for the octet. Now let us check. 1, 2, 3, 4, 5, 6 and these two bonding electrons 6 plus 2, 8. Octet completed. Now for this 1, 2, 3, 4, 5, 6, 7, 8. Octet completed. And for this O, 4 are free and 4 are busy in the bonding. 4 plus 4 totally 8. So 8, 8, 8, fantastic structure. All attained octet stability. So that's why this S has given one electron to this one, just for the attainment of stability to follow the octet. So this is what structure of SO2. So here you have taken double bond here. Now some will say, why double bond here? I will take double bond here, I will make it single bond. No problem. No problem. No problem. So this is second structure. One more structure. Or I told you, no, pi electrons are not so strong, they are free, so it will fall because it is O is most electronegative, so these two electrons will fall here. So already 4 are there, now the 2 more, 6, okay, single bond, this is one more possible structure, this is already there, this is one possibility, this is another possibility. Now see this one more possibility. Here we have taken double bond on both sides, okay. So these are what I am drawing. 1, 2, 3, 4 Levy structure for the SO2 only, but which is allowed, which is most stable is the problem. No, because ultimately we have to think of stability, right? Now in this, what it says, fourth is most favorable. Why fourth is most favorable? Because it has no formal charge. Formal charge comes when electrons start moving. Here electrons are not moved at all, okay. Therefore not a single atom is having any plus or minus charge on their head, so it is neutral, you can take it as a, okay. So out of 4, this is the most stable. Out of 3, which is next stable, 1 and 3 are next favorable, 1 and 3 are next favorable, but not the 2, okay. Why? Because they have full octet around all atoms. If you see the number of electrons here, you will come to know all having 8, okay, 8, and formal charge is not that much, okay. Out of 3, only 2 are having formal charge, here and here. But in the case of structure number 2, okay, it is less stable. Why? S has incomplete octet, less than 8, and all atoms are got charges. That way they are highly charged, they are highly active. When it is active, it is more energy. But we want molecules should be in the least energy state, that is there here. So this is the best structure for the sulfur dioxide. But we can draw all these. But among the 4, the most best suitable stable structure for SO2 is this. Now ozone, O3, okay. This is the structure of ozone. I will take double bond here. No, I will take double bond here. Take, no problem. Either you can take double bond here or here, left to you, okay. That's why these two are called what? Resonating structures for ozone. Then what is this? See, to avoid the confusion, whether you take here or here, okay. So what you do one dotted line, 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 here. That means that means here this structure will give freedom to you. You are allowed to take double bond anywhere, and this is called what? Mixture of these two. And for the mixture in the biology, what we call hybrid. Which hybrid? Resonance hybrid for the ozone. So this is structure number 1, structure number 2, and this is called structure number 3, which is the most stable, because here we have liberty to move electron anywhere, so least stable. So it is not so much, it is not so active, it is most stable, okay. Now let us imagine energy of this one equal to some x. It is among the three, the least energy is with this only. Which one? It is the resonance hybrid, which has got the least energy. Now out of 2, one will have less energy. Now you have to minus. This is already least among the 3. So that is less energy. Out of 2, one is having little less, okay. It is at the microscopic level. Then this energy minus this energy, if you minus, that is called resonance energy. Resonance energy is the energy difference between what? Between out of the possible structures of a particular molecule, the one which has got the least energy, that energy minus energy of the resonance hybrid. Whatever answer is there, that is the resonance hybrid for the particular molecule. If it is more stable, less stable. For example, if I take this as 2 and this has 4, this has 3, this has 2, just understand, okay. Now this is already least 2. Out of 2, which has least? This is 4, this is 3. So 3 minus 2, how much? 1. So 1 is the resonance energy. By chance, if this is having 4, then 4 minus 2, 2. This is 4, this is 2, this is 3, this is 2. So 3 minus 2, 4 minus 2. Okay. So, or if it is having 1, you take 1. If it is having 1, this is having 3. 3 minus 1, 2. 4 minus 1, 3. If the difference is more, then it is more stable. Okay. So, but one point to remember, among the all possible structures for a particular molecule, it is the resonance hybrid which has got the least energy and most stable. For the benzene, we can take double bond, single bond, double bond, single bond, double bond. Somebody will take, I will not take double bond here, I will take single bond here. Okay, take single bond here. If you take single bond here, then you have to take double bond here. Single, double, single, double. Why to quarrel? Let us take one dotted line or circle inside. So you are allowed to take double bond anywhere. Freedom is given. So we have put circle here. So this is the least energy structure for the benzene and most stable structure. This is the what resonating structure for the sulfate. You please practice. Now there are some misconceptions, okay, about the resonance. We'll discuss one by one. Number one, the canonical forms have no real existence. Ozone you take, okay, first ozone, second ozone, they will not exist. Simply we draw. Which one will exist? It is the resonance hybrid will exist, okay. The molecule does not exist for a certain fraction of time in one canonical form and for other fractions of time in other canonical forms. That means what? At 2 o'clock 1 minute in which form it is, whether it is in structure number 1 or structure number 2 in the case ozone, or at 2 o'clock 1 minute to few seconds in what form ozone will be. So we don't know exactly. Therefore, it is very difficult to tell that in which form ozone is there, but we can say guarantee that it will be there in the hybrid form. Resonance hybrid, that is the most stable. Okay, that is the meaning of this misconception. There is no such equilibrium between the canonical forms as we have seen in the case of tautomeric ketone and enol in tautomerism that we learn. What you want to say here? There is no equilibrium at all. Means between the two ozone structure, sometimes in this form or in this form, left right, right left. So there is no equilibrium at all. It is only the resonance hybrid of ozone exists. Okay, right. So the molecule SS has a single structure. What is structure? Single structure, which is the resonance hybrid that only exists. Other forms will not exist. So of the canonical forms and which cannot as such be depicted by a single leaf structure. Okay, good. Now we will go for final conclusion. Resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of the in a single canonical structure. So if the molecule goes for the resonance, then what happens here? The free electron is made busy. It is busy in some work. When it is busy in some work, it is spending some energy. So it will go to least energy state. So more stable. So resonance will give you stability. Therefore, they go for the resonance. Resonance averages the bond characteristics as a whole. That means bond length, bond angle. So they are average bond, not in one angle, not in the double angle, single. It is the average between the single and double in the case of ozone. So that means resonance will give us idea that bond parameters are averages. Okay, this is what our today's conclusion. Thus, the energy of the O3 resonance hybrid is lower than either of the two canonical forms 1 and 2. This is our today's conclusion. Let us believe in the fact, not in the myth. Okay. Thank you, my dear students.